Hey everybody, welcome to Bill Sky, the Assembly Guy. And what we're going to look at today is one of the things that I just absolutely love about assembler language or any kind of a language, whether it be C, C++, anything that's compiled, and even interpreters do this, is the stack. Now the stack is the heart of your assembler program, but also it's the heart of your C program, your C++ program, your COBOL program, your Fortran program. Any compiled language uses the stack. It's just the way it is. The stack is the center of data movement between functions and variables and the CPU. You use it to back up things. It's really cool. Let's take a look at what the stack's all about. So the stack is a data structure that resembles a stack of dinner plates. And I'm sure you've all seen a stack of dinner plates or maybe lunch plates where the one that you most recently washed goes on the top, the one that you last washed or the one that you longest ago washed is on the bottom. It contains data used by the CPU and your program. The data is used in the stack for passing arguments to functions, allocating temporary variables in your functions, backing up data. It's just a really useful data structure. It also is the heart to keeping track of the return address when you call a function. So when you call a function, how does the program know when you leave that function and go back to the main or the other function that you called it from? How does it know where to go? Well, the address of the line after the call is put into the stack. That's the mechanism down deep how functions return when they're done processing. And also it can be used for temporarily backing up data during the execution of your program. So the stack is what we call a last in, first out data structure. That means that the last item you put in is going to be the first item that you take out. It's kind of like lining up to go see a movie, and the person at the back of the line, the last person that entered the line, is the first person to get a ticket to the movie. Ugh, horrible, right? Well, a normal line where the first one in line is the first one to get a ticket, that's called a queue. But a stack is the last person in the line is the first one to get a ticket. When you place data onto the stack, it puts it on the top of the stack, and that is pointed to by the stack pointer. When you retrieve data from the stack, you also get it from the top of the stack, which is what your stack pointer is pointing to. So just like a stack of dinner plates, you never take a plate from the bottom, you always take a plate from the top, unless of course you're trying to build up your muscles and you want to lift up all the plates, or maybe you're a little bit, like me and you want to make sure that all the plates get worn the same amount. Oh my God, my wife would kill me if I did that quite often. But you never put a plate onto the stack from the bottom. You always put it up on top. Plates are heavy, right? Well, the data's not heavy, but that's the way it is. That's the way a stack works inside the CPU and in your program. Now, what's weird about this, though, in a computer program, is that you would think that the top of the stack, where the most recent thing you put into the stack, has a higher memory address, because that's really all the stack is. It's just a memory. It's almost like an array of 4, 8, or 16 byte words. And you might think that the address is higher as you add things to the stack, because the stack gets higher as you add things. But that's actually not the case. As you add things to the stack pointer actually gets smaller. It actually gets smaller. So let's say if your stack starts at address 100 and I add a 4-byte word onto that stack, my address for that item will now be 100 minus 4. So it's kind of like the stack is flipped upside down, which a lot of textbooks show you is that the top is actually on the bottom and the bottom is actually on the top. So the stack is actually flipped when you're talking about the address. So as you can see here, the top of the stack is maybe address X. The bottom of the stack would be address X plus the number of items in the stack N times the size of each item in the stack. And if you're a smart programmer, everything you put in the stack is the same size. It makes your code just more readable. It makes it less of a problem of having problems. So the stack width is the number of bits across. So for a 32-bit program, the stack will be 32 bits wide. For a 64-bit program, the stack will be 64 bits wide. Now, for ARM processors, that's actually doubled. And that has to do with the way that functions are called and arguments are passed to functions in an ARM processor. So when you add something to the stack, that item has a lower address than the item, quote unquote, below it, or in this case, in this graphic, above it. So as I add something to the stack, it adds it to the bottom. The stack pointer actually goes down in value. And then when I pull something off of the stack pointer goes up in value because it's moving towards the bottom of the stack. In this case, they're flipped. Now, how do I put something on the stack? I use push to put something on the stack, and I can use pop to take something off of the stack as well. I can also use the stack pointer address directly and grab data that way, which is the way functions actually work. I know this is confusing. It can be a little bit of a problem when you're first learning this, but we're going to take a look at it in actual code. So what are the registers that handle the stack? Well, you've got the stack pointer, which handles the top of the stack. So the stack pointer on an ARM processor is SP. The stack pointer on an Intel processor for 32-bit is ESP. For 64-bit, it's RSP. Then you've got this thing called a base pointer, which is the bottom of the stack. It's also called a frame pointer, and that tells you how low in the stack you're allowed to go. Now, you can always go below that, but you're going to cause all kinds of troubles if you do. Nobody's going to want to buy your product. So the EBP, RBP is the bottom of your stack in Intel. In ARM, it's the R11 or X29. R11 and 32-bit ARM, X29 and 64-bit ARM. And then in ARM, the SP register is the top of the stack. And you're going to use that a lot. So as you add things to the stack pointer changes. So if I push, as you can see right here, the stack, before I do my first push, the stack's address is 28. If I push the number 100, hexadecimal 100 onto the stack pointer goes down by 8 bytes because we're dealing with a 64-bit program here. Now I use the small number 28 as the top of the stack, so it's easy to see the subtraction of 8 from it. However, that number is much, much larger than that. So after I push 100, the stack pointer changes to 20. After I push 200, the next one, remember this is hexadecimal, 8 from hexadecimal 20 is equal to hexadecimal 18. So it goes down 8 bytes each time. The stack pointer changes its value each time. Now on ARM processors, that'll be 16. It'll change 16 for 64-bit apps. It'll change 8 for 32-bit apps. And that's really because, like I said earlier about the function, the way that they have functions called in ARM processors. Now, if you're on a 32-bit OS, it's 4 bytes instead of 8. So when you remove things, the stack pointer increases in value. So at the beginning of this, we have all those things we have the top of the stack, or I should say the bottom of the stack is up on top of the screen. We have the top of the stack down below. The top of the stack is now 300H because the stack pointer is pointing to 300H. So when we pop 300H off the stack pointer goes up in value by 8. So now it becomes 18. If we pop 200H off of the top of the stack pointer goes up by 8, which would be 20. If we popped the 100, the stack pointer would go up in address to 28. So it goes up and down depending upon your pops and your pushes. Now I think what we should do is we should demonstrate this in a nice little program so you can actually see it working. And let's do some pushes and pops on our Intel program, and then we're going to go ahead and look at the ESP and or the RSP registers as we do that. So let's get going with that demo. Okay, so let's try to do this in some code. What we're going to do is we're going to do it in Intel 64-bit first, and then we're going to do it in ARM 64-bit. So let's do the Intel first. So before we do anything, let's add some strings here, because instead of debugging this, I would actually like to to print out values so we can kind of examine them without having to go through the debugger. So I'm going to create some strings here. I'm going to say stack pointer before push pop. And this is always good practice. And I want to use the Komanetsky functions for this. Stack pointer after push. And I'm going to line up the strings so it's kind of easy to see the values so they're all kind of lined up together. And pop prompt, I'm going to define byte stack pointer after pop. Let's get that lined up there. Okay, so those are simply strings that I'm going to be printing on the screen. So let's go ahead and save and build that. All right, let's go down here. Now we're printing our opening prompt. That's fine. I'm going to put some data into some registers that I'm then going to push onto the stack. So I'm going to say move into RAX 100H, keep them simple, move into RBX 200H, and move into RCX 300H. So we're just going to put some data into some registers, and then we're going to push those registers onto the stack. So what I want to do is I want to print this first, and then after I print that, I will go ahead and start doing some pushes, and then I will print the stack pointer each time after I do a push and each time after I do a pop. Okay, so let's push. Oh, and I don't know if you knew this, but you've been using the stack every time you've used my functions because you've pushed things onto the stack. So I'm going to say push start prompt. I'm going to say call print string. So let's print that start prompt. Then I'm going to push the stack register. Now RSP is the 64-bit stack register. On 32-bit it would be ESP. On ARM it would be SP. So I'm going to push SP, then I'm going to call print, gotta be capital print 64-bit num hex, and then call print ML. Now before we do anything more, let's just go ahead and build and run this. All right, here we go. So there's my welcome prompt. I printed stack pointer before push pop, and again, you can find that right here. That's our start prompt. So we printed it right there. And then there's the value of the stack pointer. That is the top of the stack pointer. That's when you start pushing things onto the stack, it goes into that address, and then the stack pointer goes down. Now I keep saying that, but I haven't proved it yet. Let's take a look. So now what I'm going to do is I'm going to push something onto the stack. So I'm going to push RAX. That autocorrect is driving me crazy. Push RAX. And then what I'm going to do is I'm going to copy all of this. And instead of the start prompt, I'm going to use push prompt. So I want to print the push prompt. So we push a number onto the stack, and then we print the string, and then we push the stack pointer onto the stack to see if it's changed, and then we call the print 64-bit num hex. So let's build that. Built just fine. Now let's run it. All right, so let's take a close look at this. So what we have here, we have the stack pointer before any pushes or pops. That's the address of the stack pointer. Then we have the stack pointer after we did a push, and what happened to the value of the stack pointer? It went down by hexadecimal 8. So it went from 30 down to 28. Now hexadecimal 8, I believe is, what is that? 8, is that 8 bytes? Yep, I believe that's 8 bytes. Is that 8 bytes? Oh, it went, well, what is hexadecimal 8 equal to? It's equal to 8 bytes. So 30 minus 8, hexadecimal 30 minus hexadecimal 8 is hexadecimal 28. So you can see how it's changing. Now let's go ahead and copy this once again. And instead of RAX, let's push RBX. And let's do the same thing for RCX, because those are the 3 registers that I put data into. And let's go ahead and build that. Let's run it. And you can see each time I push something onto the stack pointer's value goes down by hexadecimal 8, which is basically the same thing as decimal 8. But you got to think about it as hexadecimal because 10 minus 8, hexadecimal 10 minus hexadecimal 8 actually ends up being hexadecimal 8. You can do the hexadecimal math if you'd like. Now, let's take a look at pops. What happens when we do a pop? So what I told you earlier is that a pop should increase the address of the stack pointer. So now the other thing I want to show you is that as you push things onto the stack, I pushed RAX, I pushed RBX, and I pushed RCX. Because the stack is a last in, first out, you have to pop them in the reverse order in which you push them. Otherwise, they won't go in the right place, unless you mean it to happen that way. But if you want what you pushed into the stack from RAX to be put back into RAX, you have to pop that out of the stack, the third pop. Because it was the first one that you pushed in 2 other ones. You have to pop out RCX first, then pop out RBX, then pop out RAX. And if you wanted to see quickly how to do that, you would just say pop RCX, pop RBX, pop RAX. And actually, let's try that out. So I'm going to go ahead and I'm going to move into RAX 0. I'm going to move into RBX 0. I'm going to move into RCX 0. So I'm just moving 0 into there so you can actually see the value of RCX, RBX, and RAX getting their values back. And remember, RAX has 100, BX has 200, CX has 300. Now we're going to debug this so you can see that. And oops, it looks like I don't have KDBG installed. I need to get that installed. Okay, now that I've got KDBG installed, let's try it again. And let's go over and take a look at our code here. And we're going to jump all the way down to this right here, or move 0 into RAX. And we're going to go to the registers display. So I move 0 into all of those registers. You can see how I moved 0 in there. Now we're going to pop RCX, pop RBX, and pop RAX, and they have their values back. So remember, when you pop out of the stack, it has to be in the opposite direction that you pushed. If I said pop RAX, pop RBX, and pop RCX, RBX would have the original value, but RAX and RCX would be flipped. So remember, always pop in the opposite order in which you push them. All right, so let's do some popping. Let's do some printing of our popping here. So we're going to move 0, and then I'm going to say, I'm going to pop RCX. And instead of push prompt, I'm going to say pop prompt. And all we're doing is we're just now going to print the value of the stack pointer after our pops. That's all we're going to do. And we just want to make sure, or I just want to prove to you how the stack pointer address changes. And so it starts at F0, it goes down to E8, it goes down to E0, and then it goes down to D8. Those are the 3 pushes. Then as I do the pops, it goes back up to E0, it goes then up to E8, and it goes up to F0. So that is the pops, and that's how you can see the stack pointer moving around as you push and pop things. Okay, that was our Intel demo, and the reason I did the Intel demo first is because Intel has some really nice, or I should say x86-64 has some really nice commands, push and pop. However, ARM processors do not have that. So what I am going to show you is I'm going to show you how to write a little macro in your ARM assembler to imitate the push and the pop functions or statements in Intel in ARM. But I need to show you the overview of what happens. So as I said, on ARM processors, there are no push or pops instructions. So you have to manually subtract. As you push something or put something on the stack, you then have to subtract a value from the stack pointer. In this case, 16, because we're going to be working with a 64-bit application, and in ARM, the stack is aligned on a 16-byte boundary. So it might be a little bit of a waste of space, but it's very important if you're going to be doing function calls and things like that. Just take my word for it, it's the best way to do it. So let's take a look at that demo. All right, so what we've got here is I've got an ARM, 64-bit ARM assembler language program here. And now we're not going to do prints of our variables, of strings, and of the things that we pop or push, or the stack pointer, because you already see how the stack pointer works. What we're going to do here is that we are going to actually just do the pushes and the pops. The stack pointer works exactly the same in ARM. If you skipped ahead and you didn't watch that, it would be very good for you to watch it on the Intel version, because it's exactly the same, except the values. On 64-bit, the stack increases or decreases by 16 instead of 8, like on Intel. And on 32-bit, the stack pointer increases or decreases by 8 instead of 4, as it would on Intel. So let's go ahead and play around with this, and then we're going to take a look at a macro that will allow you to actually do a push and a pop just like you would do in Intel. Very, very useful. So what I'm going to do is I'm just going to move some data into my registers just like I did on the Intel. So we're moving some data in there. I always love to build to make sure I don't accumulate errors. All right, so how do we put the first item onto our stack? Now I'm going to put a comment, initialize the registers. And you know, I do this a lot on ARM just because ARM is so different from Intel. I'm not as used to it as I am in Intel, so I always like to put a lot of documentation. All right, so what I'm going to do is I'm going to store the register x0 to the dereferenced stack pointer. So store x0 to the stack pointer memory address. You probably could have said that a little bit better. And now I am responsible for now decreasing the stack pointer by the width of the stack, and that would be 16. So I'm going to say subtract the stack pointer, subtract from the stack pointer 16 and put it back into the stack. Go to the next location on the stack. So that's x0. Let's do x1 and x2. So what's nice is copy and paste makes this really easy. And you always want to make sure you update your comments. So that'll push things onto the stack. These two statements right here are basically what a push does in the Intel assembler language. Okay, so let's go in and I'm going to move into x0, 0. I'm going to move into x1, 0, and I'm going to move into x2, 0. And all we're doing there is clear out our registers. Just clear them out. Some of you might be asking, why do I put these blank comments there? Because when I do this, it means that this, clear out our registers, not only includes this statement, but also these two. So that's kind of like a continuation of a comment. That's why I do that. Okay, so why are we doing all this? Because I want to demonstrate it in the debugger. So let's go ahead and save and build it. Now remember, you have to pop things out of the stack in the opposite direction that you pushed them. So we're going to pop x2 first, then we're going to pop x1, then we're going to pop x0. Now, how do we pop x2? Well, the first thing we have to do is we have to do the opposite of the way we pushed it. So instead of a subtract, we have to say add to sp, comma 16. And then we say load a register x2, the dereferenced sp. So what this is going to do is it's going to move my stack pointer to the beginning of the stack entry where x2 was stored. And that's what the plus 16 is going to do. And then it's going to pull that data out and put it back into x2. So let's copy and paste that, and let's do the same thing with x1 and then x0. Let's make sure we have our comments go to the beginning of the previous value in the stack. Pop the data from the stack. And I could put those comments on every line. I really recommend that you do something like that. Okay, so let's build this. And now let's debug it. And I'm going to create two terminals here. I'm going to open it as a tab. So here I'm going to say make debug1. And here I'm going to say make debug2. Now before I do that, let me make this a little bit higher. Okay, so there's my code. Oh, one thing I forgot to do, you should always do in your code is, especially ARM, right after a SVC, you should put a no op in there. So it does, the debugger doesn't jump and execute the next line of code automatically. So it's always a good idea to do that. And I had to rebuild it. Okay, so let's go through here. All right, so now we're on the move 100 to x0. We're going to be looking at x0 there. It's got 100. We're going to move 200 to x1, 300 to x2. Now we're going to start pushing things onto the stack. Now, if you want to watch the stack pointer go up, I can scroll down and look for the SP. There it is right there. And I'm just going to say step. Notice how it has not gone down yet, but now notice how when we subtract, we now are down to 20. Because decimal 16 bytes is the same as 10 hexadecimal. So we're storing stuff onto the stack. The stack pointer is getting smaller each time we store something onto the stack. So that's kind of the same way we saw it in Intel. So now let's zero out our x0, x1, and x2. And now we're going to pop off of the stack. So we're going to add 16 to the stack pointer, and we're going to load. There's the 300 in x2. There's the 200 in x1. There's a 100 in x0. To me, that is totally cool. Now, but instead of having to do this, wouldn't it be nice to have a push and a pop? So I'm going to show you how to create a macro in ARM assembler. And you can do the same thing in Intel, but there's no reason for push and pop because we already have that. So let's set up that macro right now to make your coding a little bit easier. Okay, so instead of having to do this for our pushes, and then instead of having to do this for our pops, let's write some macros so we can just say push and pop, just like we did in Intel. And the way that I'm going to do this, I'm going to go all the way up here to the very top, and I'm going to say .macro, and I'm going to give it a name of push. It's going to have a single argument. I'm just going to call it xn. I could call it x1 if I wanted, but I'm just going to call it xn. And what does our push actually, what do we have to do to push in ARM? I have to do those two lines right there. So I'm going to go up here and I'm going to paste those. And I can put comments in there if I want. But instead of x0, I'm going to say \xn. Now the reason for that is I'm going to say push x0. x0 will be stored in xn, so when I say \xn, it'll replace a \xn with x0, x1 or x2, however I do it. So that's our first macro. Let's say you have to say .end macro. Now I'm going to build this to make sure build's okay, and I haven't used it yet. But let's do the same thing for pop. So I'm just going to copy that, and I'm going to call this pop. And if you remember, we didn't subtract anymore. We added, but we also did them in the opposite order. So we added it. And instead of str, we're going to say load register. Now you might want to change your comments, but for now, let's just go ahead and make it. And now let's try out one of these. So I'm going to comment out these two lines of code. And right below it, I'm going to say push x0. Actually, let's go ahead and do that for all of these. because I'm pretty confident this is going to work. I might be confident because I rehearsed this before I did this video, so it better work. So let's go ahead and build it. All right, looks good. Now we're going to go ahead and zero out our registers in our code, and now we're going to comment out all of these. There's got to be a better, faster way. Okay, so now let's say pop x2. Then we're going to say pop x1 and then pop x0. So how does this macro work? When the assembler sees the word pop, it says, oh, wait a minute. When I was preparing this program source code, I noticed that there was a, well, what were we looking at? We're looking at pop. It doesn't matter. Let's look at the push. The assembler says, I remember that he created or she created a macro called push. So it's going to take the code inside the macro and it's going to replace this push with that code. I'm sending x0. x0 will go into the xn macro variable, and then the str\xn will be replaced with str x0 in that case. So let's go ahead and build that and make sure it works. Let's debug it. Okay, so let's step through. You see what's happened here? It has actually taken the macro and expanded it into the real code, as if you had typed it in. But the cool thing about a macro is you only have to type it in once, and now you can do it anytime you want. And I've coded this push and pop so many times, I just had to create a macro to make it easier. So I'm just going to step through this, and we're going to be watching x0, x1, and x2 to make sure that this works. So I zero it out. Oh, there's the 300, there's the 200, and there's the 100. Bingo. So our push and our pop macros work great for us. So I've already mentioned this in the Intel demonstration, but it's well worth mentioning it again. How do you use the stack? Well, when you push things onto the stack, whether it be for backing up your data and your registers, and that's a perfect use for the stack, is before you process your data, as you can see here in the middle of this code, I saved the registers that I'm going to be changing. And then at the bottom, so I push them into the stack to back them up, I process my data, I do whatever it is that I'm doing, and then when I'm done, I pop them from the stack to make sure that they are the exact same values as when I first got a hold of them. So very, very useful in x86-64. And you want to do the same thing in ARM. You can see there's a lot more code there, but if you use my push and pop macros that I showed you in the ARM demonstration for macros, you won't have all that code. It'll actually generate all that code, but you won't actually see it in your program. And you want to do the exact same thing on ARM. So, with that said, that is the stack. You're going to be using it a lot when we talk about functions, which is the next discussion we're going to have in this series of videos. And then a couple of videos or a couple of chapters later, we're going to get into real details as to how this works. Hope to see you at those videos.